I like to think of ATP as kind of like metabolic arcade tokens. Just like at an arcade, you can cash in a bunch of different forms of money. You can have dollar bills, you can put coins, you can have tens and twenties of bills, maybe even different currencies. And you stick them in the machine and it spits out a bunch of the same arcade token. And then you can go and you can play that arcade token anywhere. Similarly, our bodies and the bodies of basically every organism can break down various fuel sources. So we're talking lipids and carbs and proteins. Break all of these different fuels down, and now you have this ATP that's holding on to the energy that was held in those molecules. And now you can use that ATP. Various molecules, various enzymes, all are specialized to use this same ATP molecule to do stuff that otherwise might not be possible, at least not thermodynamically favorable. And once those enzymes are holding on to that ATP, they don't care where that ATP came from. And so can kind of contribute to this big pool of cellular energy from a variety of different sources. But where is this energy actually, like, how is it actually stored in this ATP? And how are we using it usefully?
It's a common misconception that we get energy from ATP by breaking a bond. In fact, breaking of a bond is actually always going to be endergonic, that is, it requires energy. But the key is what we get in return. There are inherent reasons why ATP hydrolysis is favorable, as well as the fact that our cells take this thing that's already favorable and it makes it even more favorable by stocking up a ton of ATP, leading to high ATP-ADP ratios, so that if you think about ATP hydrolysis, we have a ton of reactants, not much products, and that way we're able to kind of tip the decks in the favor of keeping things far from equilibrium so that we can take this reaction that was already favorable, make it even more favorable. But our bodies have to actually expend a lot of energy in order to keep these levels high. But first off, let's start by thinking about what's inherently favorable about this breaking of ATP. Again, it's not that breaking that's favorable. Instead, it's what we get in return. When we hydrolyze ATP, we don't just have to think about the ATP, we also have to think about the context that it's happening in. When we hydrolyze ATP, basically we're doing this in water. So we take these bonds that were in these ATP, and now we're going to be able to form more bonds with water. So we get hydration. We're also able to basically free electric repulsion. We have those three phosphate groups that are kind of like these negatively charged groups being held together. I like to think of it as a tightly clamped spring. Just as if you had a spring, you were trying to clamp it, and you had some sort of like ping pong ball at the end or something. It'll take you energy to kind of like hold that clamped. But if you release that clamp, well, now your ball is going to go flying across the room. Instead of shooting balls across the room, our cells do things like powering unfavorable reactions by coupling the hydrolysis of ATP to those things. So once we basically release that repulsion, a couple things can happen. One is that we can get like hydration. So basically we can have water molecules form bonds with all of those ATP parts that were released. And this hydration, basically now we're making bonds. If we said that it took energy to break bonds, well, then we get energy when we make bonds. And it's not just covalent bonds that matter, it's also these interactions. By forming like hydrogen bonds and all these like ion dipole interactions with the water, we're going to get an enthalpic gain. Additionally, we can get some other stuff. One is resonance stabilization. So the phosphates are resonance stabilized. Basically, all those oxygens are sharing electrons, but they can do this better if they're not like tied to one another. So in a free-floating phosphate group, so in one of these like orthophosphate groups where you just have like a phosphorus and oxygens and it's not tied up by being held next to other stuff, you get better resonance stabilization. And when you get this resonance stabilization, that makes molecules happy. When you do the hydrolysis, you relieve the charge repulsion between these negatively charged groups. Then once you've released that orthophosphate, now you get this resonance stabilization. You can also get hydration with water, and you can get ionization. You can go from this ADP2 minus to this ADP3 minus. Basically, you deprotonate this, and again, this is going to be favorable, releasing even more energy. So altogether, all these effects are going to combine to give you a combined delta G naught prime of about minus 30.5 kilojoules per mole, or about 7.3 kilocalories per mole. And that's just if you attack the gamma phosphate group. If, however, you attack one of the other positions, you can get even more energy. Say you transfer an AMP molecule. Well, now you're left with this pyrophosphate. This pyrophosphate, these two phosphates all together, well, here you still have this negative charge repulsion to deal with. We broke up this one, so we freed some repulsion, but now we have another place we can free repulsion. And if we free this repulsion, we'll get even more energy. We can use this to offset the cost of even more energetically expensive things, like joining together DNA nucleotides or things like this. If you take ATP and you hydrolyze it to give you ADP and inorganic phosphate, you get about minus 7.3 kilocalories per mole. If you take that to AMP, instead, you add AMP and you release that pyrophosphate, well, now you get minus 10.9 kilocalories per mole. And on top of that, when you go and you further hydrolyze that pyrophosphate, well, now you get two orthophosphates, so you get another minus 4.6 kilocalories per mole. So by doing that, you get even more energy. So all of these ways are contributing to kind of like the inherent favorability of the ATP hydrolysis, as reflected by the delta G naught prime and by the KEQ, which remember are directly related to one another. Both of these are telling us about the equilibrium favorability, the intrinsic thermodynamic favorability. Were to mix things together at equal concentrations and then let them go and reach equilibrium, would you end up with more products or more reactants? Thermodynamic favorability and molecular usefulness is highly dependent on the concentrations, even for super inherently favorable reactions like our ATP hydrolysis. So if we want that ATP hydrolysis to be favorable, what do we need to do? Well, we need to get our Q be less than our KEQ. We're going to have to spend energy in order to do this. In order to keep that ATP being a good fuel, we have to keep the amount of ATP high. If we keep ATP levels high compared to our ADP, that means that the reverse direction, actually making ATP from ADP, is going to be energetically costly. We're going to have to put in a lot of energy and go through a lot of alternative routes in order to keep ATP stocked up so that we could burn ATP in a useful way. To put a little numbers on it, the delta G naught prime of ATP hydrolysis is minus 7.3 kilocalories per mole. And remember that we could write this equation, KEQ, this equilibrium equation, as the concentration of ADP times the concentration of inorganic phosphate over the concentration of ATP, so our products over our reactants at equilibrium. We could then go and we could actually calculate what this would be. So this would actually be like 230,000, which would tell us that we'd have so much more ADP than ATP if we were at equilibrium. But what do we actually have? In our cells, we actually have a lot more of the ATP than we have of the ADP. So you can see that instead of having thousands of times more our ADP, we actually have about 10 times more of our ATP. We have these concentrations highly stacked so that we have way more reactants than we have products. We're taking this reaction that was already inherently favorable and making it even more so. We're taking this and we're kind of creeping up this side, pushing up towards our products. You can kind of think of things like spilling over. And once they're down here in their products, well, now it's not going to be easy to go in the reverse. So it'll be hard to make ATP this way, but by just reversing this, but we've given off a very large delta G, a lot of free energy that we can use to power other things. And in fact, if we go and we calculate this, we can see that the actual free energy change in our cells is closer to about minus 11.6 kilocalories per mole that we'll actually get from that hydrolysis thanks to the concentrations being skewed so that we have this high ATP-ADP ratio. Because we need to conserve that ratio in order to conserve the power of our fuel. We don't want ATP levels to be fluctuating too wildly. We need our cells to have a reliable source of energy. And one way that we could have levels of something be fairly stable is by reaching equilibrium. But as we said, like at equilibrium, we'd have like way more ADP. And even if we still had enough ATP, well, there would be no drive to do anything. At equilibrium, there's no drive, no metabolism, no life. So instead, we can keep constant levels, fairly constant levels, by steady state. If we keep making ATP at the rate at which we burn ATP, well, now we're basically able to keep a steady source of energy. Slight challenge to this is that our body turns over a ton of ATP, as in about 66 trillion molecules of ATP that get turned over a day, meaning that basically that last phosphate, the gamma one, gets taken off and added back on 3 times per minute. So we need a way that's going to quickly keep ATP stocked up. Now, ultimately, we can use redox reactions to drive the production of ATP from ADP. We can go through glycolysis, the tricarboxylic acid cycle, go all the way through to oxidative phosphorylation, take this redox carriers, pass electrons from one thing to another, power this the pumping out of protons, the input through this kind of like dam-like thing. We get this ATPase. We're making ATP from ADP and organic phosphate. But that's a lot of work. And so if we need ATP quick, what are we going to do?
It turns out that the concentration of AMP is a more sensitive indicator than the concentration of ATP about the relative amounts of energy in your cells. Because we keep the concentration of ATP so high, small little changes in it aren't going to have a big relative change. So if we say start with the concentration of ATP, that was 5 millimolar, and then we use up 0.5 millimolar, so that would be a 10% relative change. But if we converted that 0.5 millimolar into giving us AMP, so what would happen there is basically we go from having 0.1 millimolar of AMP, since we normally don't have that much, to 0.6 millimolar, which is going to be a 600% change. And so by having molecules that respond to the concentration of AMP, we're able to help regulate the making of more energy. And so we can see that basically if our AMP goes up compared to our ATP, then what's going to happen is we're going to need to go and we'll want to make more ATP. But if we go the other direction, we're going to want to make less ATP. So this is protein called AMP activated protein kinase, AMPK, that we'll talk more about, responds to decrease in the ATP-AMP ratio by phosphorylating key proteins and regulating their activities. And the end result of this is that it's going to lead to higher concentration of ATP and lower concentration of AMP. So your AMP goes up. What's going to happen is that this is going to activate the AMPK, which is going to increase the glucose transport and activate glycolysis and fatty acid oxidation. So basically, it's doing all that stuff to make more ATP. And then it's also going to suppress the energy requiring processes such as synthesis of glycogen, fatty acids, cholesterol, and protein. Our muscles also have another way to get energy on the fly. There's this molecule called creatine, and it's actually an amino acid, but it's not one of our alpha amino acids like we use in our protein making, but it does have a amino group and a carboxylic acid group. And what can happen is this kinase called creatine kinase, or CK. When ATP levels are high, it can take ATP and it can transfer a phosphate group onto creatine to give you phosphocreatine. This is going to be favorable when those ATP levels are high, when your reactants are high, when they're higher than you would have at equilibrium, you're going to be driving to the right, making more phosphocreatine. But now what's going to happen is when ATP levels are low, it gets transferred back to ADP to make more ATP. We had talked about with the ATP hydrolysis and stuff, how its power came from being far from equilibrium. And we started with a very negative delta G. So even we were always going to be favorable unless we had a ton of like basically really crazy amounts of our ADP and stuff. But if we have a reaction that's kind of more on the fence, well, now we're able to kind of respond better to changes in the concentrations. And so by having a reaction like that of creatine kinase that can kind of go back and forth more easily, then we're able to respond better to changes in concentrations. And so we can say, like, if we have high ATP, let's go ahead and make phosphocreatine. And then if things get low, if we need more ATP, we've got that phosphocreatine. Now we have more of our products than reactants that would be wanted at equilibrium. And so now we're going to go the other direction because we're adding or removing our reactants, controlling the direction of this. You have to actually make or eat more creatine because these can also non-enzymatically convert into a molecule called creatinine. So you might have heard of that. Basically, your kidneys filter it into your urine, so you pee it out. But if your kidneys are having problems, then it doesn't get like peed out and stuff. So doctors can check creatine levels to see if all is okay with them. And creatine itself is made from like amino acids and it's cool, but I'm not going to go into that. Your cells are able to have different levels of ATP and ADP and AMP and creatine and all these stuff. So the concentrations of all these are going to vary from cell to cell, depending on what types of stuff that they need to be doing. So you can see that like in a muscle cell, they have a lot of ATP, and they have a lot of the phosphocreatine. So they're stocked up in case they need to do things. But in something like blood cell, basically an erythrocyte, they have a lower concentration of ATP. They don't need to be doing all that energy making stuff. And so they have lower concentrations of these, none of the phosphocreatine. And by having like controlling these levels, our bodies, like we saw with that kinase, they were able to kind of control different molecules like allosterically often by having ATP or AMP or ADP kind of bind to part of the enzyme, get it to change shape, change its activity. So it goes from being more or less active in things like this. And this is going to help us respond to levels of ATP and ADP in order to know like, okay, well, there's plenty of energy around. Let's go ahead and let's make some stuff. Or, oh, dude, don't use up all our ATP. We're running low. So maybe we should actually start breaking down sugar. And so we'll talk much more about this regulation and the different pathways. Phosphate groups, as we mentioned, they got that good resonance that can go on. They can get good hydration and this sort of things. It's not just ATP that's able to do this, but ATP is kind of like this universal currency that if all these enzymes are able to, all these molecules are able to use it, then it makes sense to like, once you specialize in one thing, why change? But we will see that like GMP is going to be used for various reactions, as well as once we put a phosphate group onto something else, well, now we have something that can have an even greater free energy. Like look at this phosphoenolpyruvate that we'll look at. It's like a minus 14.8 kilocalories per mole. And so that's going to be like even more favorable than our ATP. It's really important that ATP occupies this sort of like intermediate between these like quote unquote higher energy phosphate compounds and those lower ones. This is going to make it so that we can actually make it. If ATP was the highest energy, it would be really hard to actually go and make it. But by having things like these phosphoenolpyruvate with this really big negative delta G, this minus 14.8 kilocalories per mole, by having that, well, now we have a way where we can actually go and charge up that ADP without having to go through the whole electron transport chain. And so we'll see how the bulk of our ATP making is going to happen through that electron transport chain and how we can basically siphon all of these electrons from all these various pathways into there. But along the way, we're actually going to be making ATP, such as in glycolysis, such as using that phosphoenolpyruvate in its high energy phosphate bond in order to directly phosphorylate ADP to give you ATP. So we're able to make ATP without having to go through the electron transport chain, without having to have oxygen present. And so this is how you can get like fermentation and stuff going, and you can use that to make energy without the electron transport chain. But then the big problem with that is actually regenerating the NAD. And so we'll talk more about that. But bottom line is ATP is in this kind of like intermediate zone so that it is able to get the phosphate group from higher energy things like the phosphoenolpyruvate, like the 1,3-bisphosphoglycerate, like our phosphocreatine, and then donate it to other molecules. And this is going to help us power reactions. So we were talking about ATP hydrolysis. So like taking ATP and adding water, and voila, we get ADP and inorganic phosphate. But typically that's not what happens. Instead, what happens is that the ATP is going to get transferred in a series of steps rather than just getting hydrolyzed. So in the first step, what we typically have is that we transfer one part of the ATP molecule to a substrate molecule or an amino acid residue, and this is going to activate it. Then what can happen is that you get displacement of the phosphate-containing moiety, generating PHI, PPI, or AMP as a leaving group. And so by doing this, you're adding a better leaving group. And so we can't just go directly from like glutamate to glutamine, like the amine group, like attacking. That wouldn't make a good leaving group if what it's kicking off is an OH minus. But if instead we can take the energy, we can transfer a phosphate group from ATP onto here. Well, now what we're doing is we're making a site that is then going to be easier to displace, because if we displace this phosphate group, well, now we've got this resonance stabilized thing and all is going to be happy. So ATP can donate phosphoryl groups. So that would be phosphoryl is basically just these three oxygens on a phosphate. This phosphoryl basically, because it's not an actual phosphate, if it was a phosphate, it would actually be transferring all 4 oxygens. But what we see is that basically one of the oxygens is going to be from the original attacker. And so you're transferring a phosphoryl group. You can also attack, so that was if you attacked the gamma position. So we can talk about like ATP as having this 3 phosphates, alpha, beta, and gamma. The gamma is the farthest one. And if you take that, you're transferring a phosphoryl group. And this is like what kinases do. If you attack the middle phosphates, that beta position, you're going to transfer a pyrophosphyl group, and you're going to end up with an AMP left over. So here we ended up with an ADP left over. Here we ended up with an AMP left over. And here, if we attack this first position, well, now what we're doing is we're actually transferring this whole AMP group, and we're getting left over this PPI, this pyrophosphate. And so these interactions, they're taking place like SN2 reactions, where that phosphate is going to be a really good electrophile because those oxygens are pulling electrons away from it, making that phosphate really electrophilic and vulnerable to attack. Once you have that added on, well, now it's going to be a great way for you to like modify molecules. So with a kinase, what we're doing is basically we're attacking that gamma position, that last phosphate, and adding a phosphoryl group. And this is really great because then what can happen is you're adding this like negatively charged group. You can get molecules, you can make a better leaving group. You can modify the action of enzymes. You can add binding sites, all these various things by having this modification that you couldn't put on, that wouldn't be possible without having a kinase. So it's not like you couldn't add it directly when you're making the protein. Instead, it's a post-translational modification. And it can be added by kinase and removed by phosphatases. We also see that we will do things like use ATP in order to allow us to join together molecules. So like amino acyl tRNA synthetases, basically they're responsible for actually putting amino acids on the transfer RNAs in order to bring the right amino acid to the ribosome. Instead of directly adding the amino acid to the tRNA, which again, there's not a good leaving group. You would have to kick off an OH minus, which would not be a good leaving group. But if what you can do is instead first attack the ATP, now you can lose this phosphate containing group that's then going to be a good leaving group. This is going to be a great leaving group, this AMP. So if you transfer the A and P on first, and then you can attack it more readily, you can basically get a better leaving group, and this is going to be a favorable reaction. Even though overall, you're basically spending energy, you're spending that ATP in order to make it happen. You can also see like DNA polymerase and DNA ligase, some various examples of how we're using the energy of the ATP in order to drive reactions. Generating intermediates, this is another common thing. You're transferring part of the ATP onto a molecule and using that as a way to make the reaction more favorable. The complicating factor is that instead of being a free floating in our cells, ATP is always hanging out with like magnesium to keep those phosphate groups from repelling one another. And this can really complicate calculations and stuff. So typically we just kind of ignore it. So let's talk about for a minute about this idea of kind of like energy coupling. So imagine that you have an inherently unfavorable reaction. So basically you've got your delta G, something like that. You've got your curve, something like this, where you're going to have your reactants at a much lower energy than your products. Now, no matter how great an enzyme is, only it's going to be able to do is lower that. So that's not going to be enough, especially because then you have to consider that if it lowers that activation barrier, then when you go and you make products, you're more quickly going to go and make reactants again. So remember that the enzyme is only going to can only affect the speed and not the direction. The speed at which you reach equilibrium, but not the direction of the equilibrium, not what's going to the concentrations when you reach equilibrium. So that's not going to work. Using an enzyme won't work. But what if we could do something where we're going to be generating a lot of energy in order to start with? And so what if we take a reaction? What if we take something where we're going to start up here and go, well, now it's going to give us enough energy to power that reaction. And so kind of like how on a roller coaster, you spend a lot of energy to go up that first one, and then you can go. So if we spend energy to make ATP, then we can use that energy from ATP. We can use it to power these other reactions, which on their own would have been unfavorable. And so this is kind of the idea of reaction coupling, is you can use a favorable reaction to drive an unfavorable one. And you can use reactions to kind of give and take intermediates in order to like pull away the products so that they drives the reaction forward even further. So there's all sorts of different strategies that can be used to kind of give energy and manipulate the levels so that things are favorable. So one of the first places we'll see this is, well, the first step in glycolysis. And so remember, glycolysis, the breakdown of sugars, the first step of it is actually going to be phosphorylating glucose by hexokinase to give you glucose 6-phosphate. This is important for a number of reasons, including trapping that glucose inside of the cell. So it can't get back out, and it's trapped. But this is going to take energy. If we were to just go and take glucose and inorganic phosphate and try to combine them, this would tell you that we had a positive 3.3 kilocal per mole change in free energy. But what if we couple that to something that's favorable? Then we can basically get enough energy to get over this. And so this is what we could do. We could couple it to the hydrolysis of ATP. We saw that with hydrolysis of ATP, we could get about 7.3 kilocalories per mole released. And what if we use that in order to drive the making of the G6P? Turns out we can do this. So remember, delta G is a state function. It just depends on the beginning and the end. And so we could go in between in all sorts of different ways. And as long as we kind of have everything cancel out, we're actually able to directly add these standard free energy changes. So in this case, we could take the standard free energy change of a positive reaction and then do the negative reaction. And then overall, you could get a reaction that's going to be energetically favorable. So yes, we had to put in energy to make that ATP, but then once we've gotten the ATP, well, now we can use it to drive reactions that are not going to be energetically favorable on their own. And so this is going to be what we see here. And so in this example, basically what we have is we have glucose plus inorganic phosphate goes to glucose 6-phosphate. If we want to make this more favorable, How can we do that? Well, we can think about like increasing the concentration of our inorganic phosphate. Increasing the concentration of the reactants is going to drive things towards products. And so how can we do that? Well, we can do that by breaking down ATP. So we can have ATP goes to ADP plus our PI, and then that PI gets used by our glucose to make our glucose 6-phosphate. And in this way, we're able to use the power from the ATP in order to power this process. So what we could do is we could go and we can actually add together those standard free energies. So remember, our phosphate groups are going to cancel out. And so what we're going to end up with is basically we can write an overall equation. Glucose plus ATP is going to go to G6P plus ADP. And now we can actually just add together their standard free energies because we've accounted for everything in this equation. And so go ahead and do that. What would be the standard free energy change for this overall reaction? So delta G naught prime is equal to minus 4.0 kilocalories per mole. So we took this reaction that would have been unfavorable, and now we've made it so that we can favor it in that forward direction. It's not as favorable if we're just burning that ATP, but it is favorable. And so it's much more favorable than if it didn't go through this pathway. So basically, although we can write it as having that inorganic phosphate, what's actually happening is that you get those phosphate groups transferred from ATP directly rather than just from a free-floating phosphate. So we could add the standard free energy changes, but it turns out that equilibrium constants, so we're like our KEQs, these are going to be multiplicative. So the KEQ for the overall reaction is the product of the individual KEQ values for the two reactions. So what are the KEQ equations for our various things? So remember that for a KEQ, it's equal to products over reactants. So that would be our G6P over glucose. And remember, we multiply these, so times inorganic phosphate. And for the ATP equals ADP, this is the one we've done over and over again earlier, times PI over our ATP. And if we think about this overall reaction, what we would have is we would have G6P times ADP over glucose times ATP. And remember that these are the concentrations at equilibrium. And so what is the KEQ for these various reactions? Now, given that we know we're given the delta G naught prime, basically, if we plug those into the equation, what we get is that for this first reaction, it's about 3.8 times 10 to the minus 3. Makes sense, we're less than 1. We know that's an unfavorable reaction. But then for the ATP to ADP plus PI, here we get a positive 2.3 times 10 to the 5th. And remember, or we get bigger than 1 KEQ, that's going to be telling us that we have a favorable reaction, which we know. So what is the KEQ for our overall reaction? Well, there are a couple of ways that we could do this. One is that we can multiply together those individual KEQs and to get a value of 8.7 times 10 to the second. So remember that this would be saying that we would have about 870 times more of our products than our reactants if this reached equilibrium. We also have gotten it directly from calculating KEQ, given the delta G that we found for the overall thing was going to be minus 4. So to review, some reactions are going to be inherently energetically unfavorable. They'll have a positive delta G naught prime, which remember is going to be saying, like, if we were to start with standard conditions, so we have 1 molar, we have equal concentrations of our products and reactants, and we let them go to equilibrium. Assuming that we have long enough time to wait, we come back, we'll find more of our products than reactants if it's favorable, or we'll find more of our reactants than products if it's unfavorable. So in the case of an unfavorable reaction, we'd find more of our reactants than our products. But what if we want to form those products? Well, we could stock up on more of the reactants, use Le Chatelier's principle to drive things to the right, but then we're going to do a couple things. One is we're going to make it even harder to go in the reverse direction, because if you make the forward direction more favorable, you're also making the reverse direction harder. And then you could have crazy concentrations of things, and it still might not even be enough to get over that bump. Now, enzymes can only do so much because they're going to catalyze the forward and the reverse directions. They can lower the activation barrier, but they can't change the difference in free energy between your starting and your finishing products, that delta G naught prime. And so basically what's going to happen, though, is that because that delta G naught prime, because the overall change in free energy is going to be a state function, what you can do is you can actually couple reactions together. So you could take a non-favorable reaction and couple it to a favorable reaction. And as long as that favorable reaction has enough energy that you need for the unfavorable one, they share a common intermediate, you can combine them in order to use the energy from the favorable reaction to power the unfavorable reaction. Now, sometimes what we want to do is we want to have reactions that are going to be very energetically favorable, so energetically favorable that it's basically irreversible. So although nothing is actually technically irreversible, there are some reactions that we consider basically irreversible because the change of free energy is so great that you can't really easily go backwards. And so we're going to see a few examples of these, which are going to serve as important like regulatory points through metabolic pathways, because you can imagine that if you can control those like go or no-go points, those points of no return, well, then you can basically control the whole thing. But what can happen then is that you're making it harder to go in reverse. So typically what we're going to see with metabolic pathways is that there are often going to be a lot of steps that are reversible, steps that have like similar, that are running at like near equilibrium conditions. Under these conditions, small changes in the concentration of your reactants or your products can lead to like what direction things are going to go. Because remember that the actual J a reaction goes doesn't just depend on that delta G naught prime, it depends on the actual concentrations. The comparison between our KEQ, so our equilibrium concentration ratio, and the actual ratio at the present moment, the Q. And so if you have a Q that is less than your KEQ, then you need to make more products. But if you have a Q that's going to be greater than your KEQ, you're going to go backwards to reactants. And so by controlling the levels of the reactants and products, you can control the direction of the reaction. But it still has to be able to overcome that delta G naught prime. And so by having reactions that are kind of running closer to that tipping point, you're able to go back and forth easily. And then by having these reactions that are running far from equilibrium, you can have a go or no-go point. And then if we want to go backwards, so if we want to, instead of doing glycolysis, breaking down sugar, we want to do gluconeogenesis, go the other direction, then we'll take a different route to go over those steps with those big change in free energy. But for these other steps, we can more easily go back and forth between them. And we can do that by changing the levels of our reactants and our products. But if we want those big changes in free energy, and if we need to do something that's really energetically unfavorable, typically what we're going to do is we're going to turn to ATP, or we're going to turn to some other quote unquote high energy compound. Remember that it's not the actual breaking of the ATP that is causing this energetic boost. It's always going to be endergonic. You're going to have to put in a little energy in order to break a bond. Because remember that whole enthalpy thing where we're going to get energy if we make a bond. So we have to use energy to break a bond. But then we get bonds to water with hydration. We get things like resonance stabilization. So there are ways in which this ATP like using this ATP is going to be inherently favorable. But typically we're not just like burning it right as is. Instead, we're transferring ATP. So we can transfer from either of the three phosphate positions, and this is going to allow us to have a nice leaving group. So we're going to see it activate various parts of reactions, make great leaving groups for when we do our SN2 type reactions. And so we're going to see a lot of examples of this when we talk about different metabolic pathways. And I don't want you to get tied up in trying to memorize all of these pathways or all these intermediates, but I do want you to kind of take a look and see how the phosphate groups and how similar things are being used in order to facilitate reactions. But remember that the big power of ATP isn't just from that inherent favorability, it's also from the fact that we keep its concentrations so out of skew, so that we have such a higher concentration of our ATP compared to our ADP and our AMP and stuff. And this is going to then allow it to have a higher potency. We can also monitor the ratio of AMP and ATP in order to have an idea, get a sense of how things are going in a cell. Do we have more energy? Do we need more energy? And then by using ATP, not only as an energy source, but also as a regulatory molecule, by having things like phosphorylation control the activity of enzymes, by having ATP and AMP and ADP act to allosterically modify various enzymes, we have all these ways where we can use ATP in other ways in order to control things like the making of more ATP. And so remember that metabolism, it's not just these straight arrows, it's not simple pathways. Instead, what we're going to have is we're going to have that complex system where things are going in all sorts of directions, and it can get really overwhelming, but you shouldn't try to memorize things. Instead, we're just going to kind of look at the connections, look at what's happening, look at the logic. And that's what I really care about you guys focusing on, is not trying to memorize all those pathways. Please, please, please don't try to memorize all those pathways. Instead, let's think about the logic, because if you can understand that logic, well, then you can apply it to all these different pathways.